All right, what's up, guys? In this video, we're going to pick up with some more calculus here, and we're going to do another example of implicit differentiation. All right, so we're asked to use implicit differentiation to find dy over dx, and we're given tangent of x plus y is equal to 2y. So basically, remember what you do for implicit differentiation is you differentiate both sides with respect to x, and every time you differentiate y, you multiply by dy over dx. And if you know your derivatives very well, you'll easily see that that's just the chain rule. So let's go ahead and start by doing that. We'll differentiate both sides with respect to x, and really that's the only calculus actually involved in the whole implicit differentiation process, is taking the derivatives of both sides at the beginning. The rest of what needs to be done is just a bunch of algebra, because you're just trying to isolate the dy over dx at that point, and that's really the only calculus that's actually involved in it, is this first step. Okay, so let's begin by differentiating. So we'll need to differentiate tangent of x plus y, but keeping in mind that every time we differentiate y, we multiply by dy over dx. Okay, so keep that in mind. So to differentiate this side, we'll need to use the chain rule. So this would be secant squared, this would be secant squared of x plus y. And then the chain rule says that we take the derivative of the inside, or multiply by the derivative of the inside, but we got to make sure we multiply by dy dx anytime we differentiate y. So this would be secant squared of x plus y multiplied by 1 plus dy over dx. And then over on this side, same principle here. This would just be 2 times dy over dx. Okay? And that's pretty much the only calculus involved, just taking those derivatives. Now all we need to do is just isolate this dy over dx. So we're just going to do a bunch of work to try to see if we can do that. The goal here, typically when you have, and all implicit differentiation problems won't be like this. Some are obviously very easy, and you'll want to start with those for your first couple examples. You're going to have, for some more advanced problems, a lot of dy over dx's. And so the goal is to get all that stuff, or to get all those dy over dx's over to one particular side, typically the left hand side, or the side to the left of the equal sign, so that you can end up factoring some stuff out. So I think the best thing to do here over on this side is just go ahead and start by expanding out the left-hand side. So if you expand out this left-hand side over here, what will you get? Well, if you expand out the left-hand side, it looks like you'll get secant squared of x plus y plus dy over dx secant squared of x plus y is equal to 2 times dy over dx. We'll then subtract secant squared of x plus y from both sides, and in that case we get dy over dx is equal to secant squared of x plus y is equal to 2 times dy over dx minus secant squared of x plus y. The next thing that we'll do is we'll subtract 2 times dy over dx from both sides, because what that's going to do is get the dy over dx over on that side. So we'll now have 2 dy over dx's on the left hand side, or the side to the left of the equal sign, and then we could end up factoring out one of those dy over dx and solving for dy over dx in that case. Keep in mind that dy over dx as well is the same thing as y prime. A lot of people don't write dy over dx, they write y prime, so I just want to mention that as well. So if we subtract 2 times dy over dx from both sides, we'll get dy over dx. It's simply going to be multiplied by secant squared of x plus y. We'll subtract 2 times dy over dx. And then over on this side, obviously that leaves us with a minus secant squared of x plus y. And now we got the 2 dy over dx's over on this side. Let's end up factoring out one of those. And if we factor out one of those, we'll get dy over dx. And if we factor one out, well, then that must mean that we got secant squared of x plus y. And then it'll be subtract 2. And then we didn't do anything to this side. Remember, that was minus secant squared of x plus y. Now, you can always check to see whether or not you factored something correctly, or in this particular case, if you factored something out correctly by simply distributing it back in. And so ask yourself, will we get that back out if we distribute back in that dy over dx? And absolutely, because we'll get dy over dx times secant squared of x plus y, which is exactly what we'll get if we distribute it in. We'll also get 2 times dy over dx if we distribute it back in. It is a minus sign there, so we do know that we factored it out correctly. And so obviously, to isolate the dy over dx, all we have to do is divide both sides by secant squared of x plus y minus 2 to get our final answer. So our final answer for this problem using implicit differentiation looks like we'll just get dy over dx, and I'm going to bring the negative to the side, and it looks like we'll just end up getting secant squared of x plus y, all divided by secant squared of x plus y minus 2. And that would be your implicit derivative. I will leave it at that. So again, implicit differentiation, much like a lot of things in calculus, it's going to take a little bit of practice before you fully get the hang of the whole process. So start off with some easy examples and then work your way progressively to some more difficult ones. This is a very important technique that you'll need in your calculus career. So yeah, so that's how you do implicit differentiation. So I'll post some more examples, so hopefully that made sense. I'll see you guys next time. Let me know if you got any questions.